In this video, I'm going to teach you PyTorch in 7 concepts. Since starting this YouTube channel about 2 years back, I have created many dedicated tutorials about writing complex learning systems from scratch. Language modeling, computer vision, diffusion for generative images, speech networks, reinforcement learning. I have done it all, and PyTorch has been a core essential component behind every one of those systems. In this video, I'll show you 7 concepts that covers everything you need to know to get good at PyTorch. You'll learn a lot about tensor programming, auto differentiation, what linear models are and how to write them from scratch. And then we're going to move on to more complicated topics, more advanced topics of creating custom neural networks from scratch to learn from images, to learn from text and even multimodal inputs. You'll also learn about how to deal with distributions and how to train models in PyTorch that also account for uncertainty, how to do logging, deployment, and everything in between. And finally, at the end of the video, there's a bonus section where I'll also talk about 10 different libraries other than PyTorch that you should also learn, which will take your game up to the next level. These are libraries that are very commonly used in production pipelines, and I've used them a lot in a lot of my projects, and I'll totally recommend you to learn it after you've learned PyTorch. Along the way, I'll also teach you some design principles that really shape your mindset about how to even develop and how to think about problems the PyTorch way. I'm really excited. This video has been a long time coming, but before we begin, I have to give a massive shout out to my Patreon supporters. We are getting close to 100 monthly paid members, and there's a lot I have to thank you for. Thank you for your support. You've been magnificent. Let's go. First, let's talk about tensors. A tensor is a generalization of vectors and matrices. It's a multidimensional array that holds numerical data, similar to a NumPy array. Unlike NumPy arrays, however, PyTorch tensors are optimized for GPU computation and can store something called as the gradient information. In the second section on automatic differentiation, we'll really understand just how powerful this gradient information is. But before moving on to those more complicated things, let's first understand what a basic tensor really does. First, we can create tensors with just random numbers like this. Much like NumPy arrays, we can also do element-wise addition, multiplication, subtraction with simple syntax like this. The next key operation is tensor transposition. This is a fundamental operation to swap the rows and columns of a tensor. And the main reason why we even use this is to set up for matrix multiplications. In Torch, we can do this with this @ sign. Matrix multiplication is pretty much everywhere in deep learning. It is the fundamental building block of linear algebra and therefore deep learning, and we'll soon see a lot of examples that uses matrix multiplications to train weights of a neural network. Next, let's look at broadcasting, a feature that allows PyTorch to perform operations on tensors with different shapes. The code here shows us adding a tensor of shape 3,1 to a tensor of shape 3. Instead of throwing an error, PyTorch will automatically stretch the smaller tensor to match the dimension of the larger one. This allows the operation to be performed element-wise, resulting in a final tensor with the combined shape of 3,3. Now, this is useful often, but behaviors like this can also introduce some random errors into your code, so make sure you're aware of this and keeping it in mind when you're writing code. Next, let's look at another basic building block of PyTorch, batch matrix multiplication. This is fundamental to training neural networks on batches of data. In the first example, we defined 2 tensors, A and B, both with a batch dimension of 10. A represents 10 matrices of size 3/4 and B represents 10 matrices of size 4/5. The operator then performs matrix multiplication on each pair of matrices in the batch, resulting in a new tensor with the shape 10,3,5. This is an extremely common occurrence if you're aware of attention mechanisms in transformers. There, often you'll have 2 sequences of embedding vectors, and you want to quickly and parallelly compute which of the pairs are most relevant to each other or which ones give most attention to each other. That's basically what attention does, and this kind of batch matrix multiplication really makes it very simple to code such behavior. Next, let's also look at batch matrix multiplication with broadcasting. Here we use a 2D tensor with no batch dimension and multiply with our batch tensor A. PyTorch broadcasts the single matrix D across 10 matrices in the same batch and repeats the same multiplication for each one. This is very common in standard multi-layer perceptrons used to project embeddings from one shape to another. Here our input had an embedding size of 4, but after multiplying with the 2D weights, we have an embedding size of 5. Next, let's quickly cover some more basic shape manipulation stuff. Reshaping allows us to rearrange the data in our tensors into different shapes. For example, we can change a 3D matrix of shape 2, 3, 4 into a flat vector of shape 24. You can imagine to use this for flattening the embedding of an image, which often also has 3 dimensions: the width, the height, and the number of channels. You can also use -1 in the reshape method, and this lets PyTorch automatically determine the dimensions. Squeeze and unsqueeze are also very important functions that basically allows you to manipulate the number of dimensions in a tensor. So you can easily go from a 3D tensor to a 4D tensor to a 5D tensors and back to a 3D tensor again. We will continue to have a look at more complex examples with tensor manipulation as this video goes along, but before that, let's have a look at another feature that makes PyTorch special: automatic differentiation, or AutoGrad. This is the main point of using PyTorch. This is how PyTorch automatically computes the gradients needed to train a neural network. Let's go. To start, we create two tensors, x and y. The key here is this parameter requires grad equal to true. This tells PyTorch to track every operation performed on these tensors and build something called a computation graph in the background. You can imagine the computation graph as a sort of dependency graph that tells PyTorch which variables are derived from which variables. When we compute z equal to x squared plus y cube, PyTorch records how z was created from x and y. And this allows PyTorch to know the information that in order to make changes to z, we need to make changes to x and y. So next, let's see where the real magic of PyTorch really happens: the backward pass. We have already calculated our final value of z, and now we need to figure out how much each of our inputs x and y contribute to that result. We simply call z.backward. This single command tells PyTorch to automatically calculate the rate of change, or the gradient. This gradient tells us how much we need to adjust each of the input, the x and the y, and how much a small change in x and y, our inputs, will make a change in our output z. PyTorch stores the gradients directly in this x.grad and y.grad attributes, and these .grad values get filled up when the z.backward function was called. And as you can see, we can instantly retrieve them. This means we never have to do the complicated math of calculating derivatives ourselves. So in other words, we don't explicitly write out the partial derivatives of z with respect to x and y. PyTorch's automatic differentiation automatically figures that out for us. Let's see a more complex graph in the next example. Now we get to chain rule, which is fundamental for how gradients are calculated when it's a sequence of operations that lead to the result. In this example, we have a chain of dependencies: x of xy, y of xz, and then z of xw. And our goal is to compute how much of a small change in our initial input x will impact our final output w. Let's see. So here we have this torch.autograd.grad function, which allows us to look under the hood and manually calculate each piece of the chain rule. Now in practice, you never actually use this torch.autograd.grad function. You just call that backward function we saw a little bit earlier, but I'm using this as an example to really drive in the point as to how partial derivatives and how chain rule works in PyTorch. So as you can see that we can compute the rate of change of w with respect to z, because remember, w is directly dependent on z. So we calculate dw dz, dz dy, and dy dx. The output shows that these values are 10, 1, and 4. And finally, to get our dw dx, we just do what the chain rule states. We multiply these individual gradients with each other to get the final gradient. That result is 40. And again, feel free to pause and read through this derivation. The result is actually correct. In PyTorch, you're going to build massive neural networks that are basically computation graphs just like these. As we pass our input through the network to obtain the output, we call it the forward pass. In most PyTorch programs, this is exactly what you need to do. Define the computation graph to convert your input into your output space. PyTorch takes care of the heavy lifting, the auto differentiation, the backward pass of actually propagating those gradients back from your output to the weights of your neural network. But obviously, we're not going to sit and write the AutoGrad stuff for each weight, right? Thankfully, PyTorch provides a way better option. You can simply call backward. We instruct PyTorch to automatically traverse the entire computation graph from w all the way back to the independent variables, in this case x, and apply that chain rule for us. So the final gradient of dw dx is then stored directly in x.grad, giving us the same result of 40. PyTorch applies the same concepts to a vector as well. So instead of inputting a scalar as x, if you just passed a vector in and activated that computation graph, PyTorch will still parallelly track all of the gradients of the input tensor, and the resulting gradient is also a tensor of the same shape as the input. This really demonstrates the simplicity of how PyTorch is crafted. And again, I'm going to repeat this portion. When you create neural networks in PyTorch, you just create the forward pass, how your input gets converted to the output. PyTorch takes care of the gradient computation step. It automatically calculates the gradient and lets you optimize for it. And we're going to soon see how this optimization actually works. Now, let's talk about gradient accumulation. This is a very key concept in PyTorch, and I have seen a lot of people get confused by it. So I have a simple example that explains how it works. So gradients are not overwritten. They are added up or accumulated on that dot grad attribute of a tensor. And this is not a bug. This is a feature, and it's there by design because it allows you to sum gradients across multiple forward passes through your computation graph. In the first step, we define y1 equal to x cube, and after we call y1 dot backward, PyTorch calculates our derivative, which is equal to 3 for x equal to 1. In the second step, we define a new dependent variable, y2 equal to x squared. Now the x tensor is still the same. We have not reinitialized it. We have just created a different output y2, a different dependent variable of x. And now if we did y2 dot backward, PyTorch calculates the gradient of x as 2. But this new gradient is added to the previous one. So if you just printed out the final value of x.grad, it's actually 3 plus 2 equals 5. This behavior is why you must manually zero out gradients with optimizer.zeroGrad if you don't want old gradients to carry forward. And notice after zeroing out the gradient, we are in fact getting the expected gradients once again of 3 and 2. If you didn't understand the significance of this step, don't worry, I have some interesting examples coming up in the next section. Just remember, zero grad is something we kind of do by default when we are training PyTorch models, and we're going to talk about it in later sections. Alright, this next snippet should be very easy for you to understand. Backpropagation totally can happen through vectors or even multidimensional tensors. And this is all due to the fact that in the end, we're defining computation graphs, and PyTorch reads these graphs and understands which tensors are dependent on which other tensors. As long as this dependency is differentiable, gradients can always flow back. Here are some examples of operation that PyTorch can flow gradients through. Note that some of these are non-continuous functions, but PyTorch can still flow gradients through them. For example, the max operator, it's not actually a differentiable function in math, but in PyTorch it is. When you're doing torch.max between two tensors, Torch does element-wise comparison and flows the gradient back through the larger value at the individual positions. In fact, Torch also has a if-else option that is differentiable. It is called torch.var. Torch.var takes 3 arguments: a condition, an input tensor x, and an input tensor y. At each position that the condition is true, the output element is taken from x, and if it's false, it's taken from y. The dependency graph of the resulting tensor z is therefore split into the values from both x and y. Alright, so now that you've understood some very fundamental concepts about PyTorch, let's look at the next section where we will get into the practical applications of these concepts by training a linear layer to fit our data. Let's go. Here, first we create a simple table of data containing house prices. This table has columns for the square foot area, the building's age, and its price. In practice, you'll have a larger dataset than this from an external source, but for this example, I'm just declaring a dataset at the top of the script. Notice how different these numbers are. Some are in hundreds, some are in tens. So we must first normalize this data. All of our numbers will then be in this nice fair range. Intuitively, this tells the neural network that capturing the variance within each attribute is equally important. Normalizing data ensures all features contribute equally into the model's training. Alright, so now that our data is clean and ready, we need to convert it into tensors. The X tensor will hold our input features like area and age. And the Y tensors will hold our target values, the price thing we talked about. Importantly, you'll see that these are constants. We did not have that requires grad equal to true thing on for these because as we're training the network, we don't want to update the X and Y values and accidentally tamper the dataset. Instead, let's just have a look at what the model will actually learn, the actual weights of the model. Here we create 2 tensors for our model's weights and its bias. And notice the key line here, requires grad equal to true. This tells PyTorch that these are the trainable parts of the model because we need to calculate gradients for them. You can imagine these two values in W to be the factor we want to change the area and age attributes of the house, and the bias is what we add on top. So our computation graph to generate the price is dependent on the constant X and the corresponding weights and the additive bias term. Again, only W and B are trainable, so they have the requires grad equal to true flag on. Now let's bring it all together to get our very first prediction. This single line of code is our model's forward pass. It takes our input data X, multiplies it by our weights W, and then adds the bias B. This is a linear transformation because all we're doing here is scaling and shifting. We are scaling the area and the age of every data point in X by the weights and then shift it by the bias term. This simple calculation produces our model's guess, which we are calling prediction or pred. After we have the prediction, our next goal is to find out how good it is. We figure that out by calculating the error, which is the squared difference between our prediction and the real answer, and take the average of all of those errors to get a single number, the loss. This one number basically tells us how far away our current model's prediction is from the ground truth price of that house. And this is the number that we are going to optimize and try to reduce this loss at every training step. Let's look at how. First, we call loss.backward. As we saw before, this is a command that tells PyTorch to calculate the gradients for all of the trainable variables. In this case, it's our weights W and the bias B. Think of the gradients as a map that tells us how to adjust W and B in order to reduce the loss and go downhill in that loss space. If you look closely at the gradients themselves, you'll see that this W underscore area has a negative gradient and W underscore age has a positive gradient. And this basically means that if we increase the value of W underscore area and decrease the value of W underscore age, we are going to see a drop in the loss. So now that we know which direction to go to update our weights, we take an optimization step. We are going to take our weights and bias and subtract a small portion of the gradients from them. The LR you see here is a learning rate, and it controls how big of a step you take in that optimization space. After this step, our weights will be updated, and if we run our model again with this new weight and again calculate the loss, you'll basically see that the new loss is smaller than the old loss, meaning that we have successfully applied gradient descent to improve our model just a little bit in a single step. This literally means that our model is slightly better and closer to the optimal weight and bias for our dataset. Alright, so let's put everything we have learned together into a full training loop. First, we initialize our weights and bias, just like before, but this time, instead of manually updating them, we're going to use a special tool that PyTorch provides called an optimizer. We give it the weights that we want it to update and also give it a learning rate, and it handles all the heavy lifting. We then create a loop that will run, let's say, 10 times. Inside this loop, we follow the same process. We run a forward pass, calculate our loss, and then call loss.backward. The loss.backward updates all of the gradients in all the dependent variables, and then for the magic, we call optimizer.step. This single command uses all the gradients we have just calculated and then updates our weights and bias for us. Right after that, we call optimizer.zeroGrad, which, if you remember our previous example, it basically calls the zeroGrad function in all of our tensors and resets everything for the next round. As the loop runs, we can see our loss value steadily going down at every step. After all 10 steps are finished, the training is complete. You can print out the final weights and bias. This is a trained linear regression model. These are the optimal values our models sort of converged on, and as expected, notice that the final model multiplies the area with a higher positive number, indicating it impacts price positively, and multiplies the age with a negative number, indicating it's inversely proportional to the price, and then we have the bias term that adjusts the output. In a real project, since we had normalized the data before, we would now denormalize it and send it back to the actual price space, but I'm leaving that up for this demonstration. Now let's move on to multi-layer perceptrons or MLPs. Take a look at this dataset. You can see it's clearly not a straight line, right? It has a curved, almost zigzag pattern. In our last example, we used linear regression to fit a straight line to our data, but that would not work here. Instead, we use an MLP or a multi-layer perceptron. Basically, MLPs are multiple linear layers stacked on top of one another, executed in a sequence, but there's a non-linear function in between each of them. Let's see how to code something like that in PyTorch. The most common way is to use nn.sequential to build our model. It's like building a simple pipeline of layers. Inside this nn.sequential, we just pass a sequence of PyTorch modules. Here the nn.linear layer is exactly equivalent to the weights and biases that we talked about in the previous example. Each nn.linear layer has an input feature dimension and an output feature dimension. So in this case, we have a one-dimensional input and we are sort of projecting it into a higher dimension, this hidden dim dimension. And then in the last layer, we are projecting back from that high dimensional back to one dimension to predict our output. But also notice that nn.ReLU in between them. It's a non-linear activation function that allows our model to learn curves and complex shapes. Without it, our model would just be a series of straight lines and could never really fit the zigzag pattern. Our training loop also looks very similar to the one we built for linear regression. But this time, we give the optimizer all of our model parameters at once. We run a loop for 200 steps. We can see the loss steadily going down, which means the MLP is successfully learning to fit the complex nonlinear shape of that zigzag dataset. Two-layer MLPs are pretty powerful, but you can increase the number of layers as well to learn even higher ordered compositional datasets. For example, datasets where there are a lot of sign changes happening like this one, a 3-layer MLP will do better. A 3-layer MLP can basically use its first layer to understand where it is in the space, and then its second layer to understand the local patterns of that particular state more easily. So the width and depth of your MLP is often just dependent on how complex your task is. So now that you've understood tensors, automatic differentiation, and the basics of PyTorch training loops, let's look at some more complex examples. We're going to ramp up in a big way. Next section, I'll be showing you some awesome torch pipelines that I've built in the past and show you how to implement some of the most well-known and useful neural networks. If you're a beginner, the goal for you is not to understand the complexities of every line of code you're going to see. It's more about to get your brains running and to understand the main takeaways about how to design these networks. And of course, as I'm explaining those networks, I will also attach individual videos that goes into details about how those networks are trained in practice and how to build them up from scratch. So if you're interested in any specific one of them, like a computer vision one or an NLP one, you can go check them out separately after you finish this video. So far, we have only talked about flat datasets where we have a table of attributes. But what happens when our inputs are multidimensional? Like for example, an image. Well, for this, we have a handy layer known as the convolution layer. I already have a couple of videos that goes over the code and theory behind CNN, so I'd encourage you to check them out. You can think of convolution layers as an automatic feature detector that captures local patterns or spatial features in your dataset. PyTorch has this convenient conv2d layer that automatically implements it for us. It outputs a bunch of small feature maps and then condenses the images information. And here's an example of that. Now the output of our convolution layer is a 4D tensor containing the batch of examples, the number of channels, and each channel having a width and a height. Then we use a command to flatten the features into a single long vector of numbers and then pass that through a linear layer where we can do additional classification tasks. The linear layer here, for example, is outputting a vector of size 10. You can imagine that you are doing a 10-way classification task like an MNIST dataset, for example. If so, the outputs of the linear layers is something we called as logits. They are unscaled probabilities. These numbers don't mean much on their own, but when we apply a softmax function to them, it converts them into a nice clean probability distribution. And if we see the output, you can see that after the softmax, each of our input data points is now converted into a probability distribution across 10 classes. To finally train a classification task, we will basically use something like the cross entropy loss to teach the neural network which probabilities to maximize when certain images are shown to it. This is how digit classifiers, animal classifiers, basically any kind of classification tasks work. You take an image, you pass it through a bunch of convolution layers to extract high-level features, flatten it, and then put it through some additional MLP layers to finally generate a probability distribution of class predictions. Here is how the code looks for a deeper CNN layer, an old architecture called the Linnet 5. Notice how the output of one CNN is passed on to the next. The max pool layer is used to downsample the image. Also notice how we have basically created a custom PyTorch module. First, we have declared this class as a subclass of nn.module. This is PyTorch's way to allow us to make our own custom layers and modules. All you need to do is subclass from nn.module, call the super constructor like this, and all the trainable parameters you initialize in the constructor will be automatically tracked by PyTorch. The next important function is this forward function. This is a special function that you must override in all of your custom neural networks. Here you define the exact steps that takes your input and transforms it to the output, and the exact layers of operation it must apply to do that. You can use literally any PyTorch function here, do tensor operation, custom layers, anything. As long as it's a differentiable sequence of operations, PyTorch will automatically construct the backward propagation graph for you, meaning you can pretty much write any custom training pipeline that you want. Next, let's see another example of a forward function. Let's look at this ResNet block. The core idea of a ResNet block is a skip connection. Think of it as a direct path of information. Instead of forcing our data to go through every single layer in a block, we just give it a shortcut to skip one or more intermediate layers. ResNets allow you to train really long CNN networks. Look at the forward function here though. We first pass our data through the two convolution layers and pass it through something called the batch normalization layer, just like a normal CNN. But here's the key. After that process, we add the output back to our original input X. So the final input isn't just the result of the layers, but a combination of the layers output and the original input. This simple shortcut makes it easier for models to train effectively, especially for long models and deep architectures. And it is just so easy and simple to write in PyTorch. And once again, after you've written this module, you can again use it in other blocks. For example, this function just calls the previous ResNet block in a loop. So you've basically just created a 36-layer deep ResNet block just like that. Also, another type of neural network to know about is the AutoEncoder style network, where you have compressed the image into a latent dimension space and then expand it back. I have a lot of code walkthroughs already about how this kind of models are trained, including models like Unit, for example. So I'll encourage you to have a look if you're interested in that space. All right, so we had a look at some of the image applications, how to create neural networks for images with PyTorch. Let's now look at some for text. RNNs or recurrent neural networks are a classic architecture. They are built to understand sequence of data, like sequence of text or sequence of any numbers. And obviously PyTorch already has a lot of useful functions and layers that lets you use them as a plug and play toy. Let's see an example. Here we are using a special kind of RNN called a GRU. It takes a sequence of inputs, processes one item at a time, and maintains a hidden state that remembers or tries to remember everything it has seen so far. Our input has a specific shape, the number of items in the sequence, the batch size, and the number of features for each item. The final output tensor has a new shape containing the embedding of the entire sequence. And again, these small modules can be used compositionally. For example, let's take a look at encoder-decoder architectures. Encoder-decoder architectures are very commonly used in sequence-to-sequence tasks. For example, machine translation or text summarization and all of that. Let's say you have a simple task where your input text is in French and you want to translate it to English. Think of the encoder as a reader. Its job is to read the input French sentence, process it word by word, and compress all of its meaning into a single dense thought vector. The decoder is the writer. It takes that thought vector from the encoder as input and starts to write a new sentence, one word at a time. It uses the vector's context to predict the next word in the sequence in English. The final class sort of brings them both together. Again, refining our idea of composing different modules together is what PyTorch is all about. It first runs the entire input sentence through the encoder to get that thought vector. Then it starts feeding that vector to the decoder, asking it to predict one word at a time. Notice how we also have an if-else and a for loop inside the forward function. During training, we use this teacher forcing trick to randomly choose whether the decoder is fed with its own previous prediction or the correct word from the real sentence. Now, even if you did not understand what this teacher forcing thing is actually doing, that's fine. Just understand that you can use for loops and if-else statements, and PyTorch is smart enough to understand how the gradients actually flows from those dependent variables, your outputs, back through the weights of the network. So again, I hope your brain is turning as you're seeing all of these code and these patterns to write model architectures in PyTorch. Of course, no PyTorch video is complete without the mention of the attention network. I have an entire video series on this topic, so I won't repeat too many things here, but here's a short summary. The attention layer passes the input through the query, key, and value projections. Then here we are calculating the attention scores by using that batch matrix multiplication method that we discussed earlier by computing the dot product between the query and the keys. And then we scale the values using the attention scores and return. You can add more stuff like layer normalization, MLPs as well, and you can also call attention layers in a sequence, much like a GPT model. Again, if you're interested in transformers and coding one from scratch, I strongly recommend you to go watch this video after you finish with this one. Of course, customization in PyTorch does not just stop at model architectures. You can also customize loss functions. PyTorch already provides a host of great loss functions that you can use for your tasks. Here are some of the most common ones that you absolutely need to know, and you're going to use it a lot. Especially mean square error loss is used a lot of times for regression tasks where the output is a continuous variable that you're trying to predict. And the cross entropy loss is another one that's extremely useful when you're trying to do multi-class classification tasks. The third one is the sigmoid cross entropy one, which is also very useful when instead of a multi-class classifier, you're just training a binary classifier. Another interesting one is the triplet margin loss function, and it's used a lot in contrastive training when you're trying to increase the similarities between positive examples and reduce the similarities between negative examples. I also want to remind you that even nonlinear activation functions are customizable. PyTorch has a host of them other than the ReLU that we have been using. Here is a list of some of the more common ones. Another important concept in PyTorch is datasets and data loaders. A dataset in PyTorch is an object that literally stores your data. It's an abstract class that you can inherit to represent images, text, audio, etc. You can also create custom datasets. You need to provide a length method which returns the size of your dataset, and a getItem method that inputs an index and returns a single data sample and its corresponding label at that index. For example, this is a custom dataset which just returns an image from a specific folder, a label, and also applies some augmentation to the data before sending it back. So any kind of pre-processing stuff can just be handled in this getItem function. The other thing is the data loaders class. A data loader is an iterator that wraps a dataset. Its purpose is to handle the heavy lifting of data preparation for your training loop. It automatically provides several key features like batching, shuffling, also things like parallel loading and prefetching is something you can also do with data loader. And just like everything you can customize, you can even customize how gradients are stored and used. For example, gradient accumulation is a technique where you effectively increase your batch size without using more memory. After processing a single batch, you don't immediately call the zero grad and optimizer.step, but instead you let the process run for multiple batches, accumulate gradients, and then call optimizer.step and zero grad. This is particularly useful when your GPU can't handle very large batch sizes directly. There's also gradient clipping, which is a technique used to prevent exploding gradient problem. Basically, if your gradients are too large, the model is going to take huge unstable steps. So if you clip by norm or clip by value, it's going to keep the training process stable and the models will converge more reliably. There's also learning rate schedulers, which PyTorch also makes it easy to do, that automatically adjust the learning rate or any other coefficient in your training as the training goes on. PyTorch also gives you a lot of options of optimizers other than the SGD that we had a look at. Here's a list of some of the common ones. The most common one is probably Adam, also Adam W. Honestly, unpacking all of these optimizers requires its own separate long 5-hour video, so I'm not going to attempt it today. Another important one that you got to know about is torch.distributions. It's a powerful package that provides a wide range of probability distributions like normal, Bernoulli, and categorical, and tools to work with them. It even allows you to train models where you backpropagate through the probability distribution. And this is a core concept to train VAEs and stochastic quantization models and even reinforcement learning like policy gradient. Here's an example of a Bayesian neural network. Standard neural networks learn fixed single-valued weights, but in BNNs, you treat the weights and biases of the network as probability distribution instead of fixed value. This is where torch dot distribution becomes critical. As shown in this code of the Bayesian linear layer, instead of defining a single NN dot parameter for a weight, you define two. One for the distribution's mean, defined by this weight underscore mu, and one for its standard deviation by weight underscore rho. The forward pass basically samples a weight from this distribution, so it's going to be different every time. And this means for the same input, a BNN can produce slightly different outputs and account for the uncertainty in the data. And here's what happens when you train Bayesian neural networks. You see they also output some kind of an uncertainty score for your network. So in places where the data points are less, you see a spectrum indicating that the network is uncertain in those regions. Another way to predict uncertainty is directly. So here in this uncertainty code, we are actually outputting two different heads. The first one is the mean of the distribution and the other is the log variance. And this allows the model to output not just a single prediction, but a distribution of prediction. And here you can see exactly how it does. Here I have a data set where the variance in the data sort of grows as X grows larger. With a simple linear regression model, you'll never be able to capture this particular feature in the data set ever. But if you ask the model to predict both the mean and the standard deviation, you can see that the model is able to branch out as X grows higher to capture the increasing variance as well. Alright, next, let's have a quick look at observability and deployment. For observability, the two most common approaches is using TensorBoard and WantB, or weights and biases. To set up TensorBoard, you just need these lines of code. You can write a new log by using this function, and after you train your model, all of your data gets stored locally in a folder, and from this directory, if you run this TensorBoard command, you'll be able to visit your local host and look at all of the logs and the training curves that you had saved previously. The other one, WantB, is something people are using more lately, but it also has a similar API and similar interface. So if you want to learn something new, I'll suggest to go with WantB instead of TensorBoard, because it seems WantB is slowly coming more and more into fashion. For deployment, it's a whole can of worms. There's a lot of ways to deploy PyTorch models, and I will make a dedicated video on how exactly to deploy. It really requires a separate video, but in this video I'm going to mention the approach that PyTorch recommends to use, which is torch serve. So to demonstrate this, I've trained this very simple GRU model that is going to do sentiment classification. I have this short data set, I define a GRU model, I pass my data through the model, and then train a binary classifier on top of it. When saving the model, it's recommended to save everything you need to save in order to recreate that same state during inference. So here I'm saving this config.json file, which contains all of the hyperparameters that is required to initialize this model. I'm also saving this vocab.json file, which contains the vocabulary that was used to actually train the model. And of course you have the torch.save thing, which saves the weights of the model as well in that path. Now, after you have saved your model, you want to run this torch model archiver thing where you pass in the model name. It's basically a tag to identify your deployed model. You pass in the serialized file, which is basically the weights of the neural network. You pass in a handler script. I'm going to talk what the handler script does in a minute. And you also pass the extra files, which contains all of the files that is required to actually run the model. After you run this command, it's going to save a .mar file containing everything that you just bundled. The handler.py file is what Torch is going to use to actually serve your model. It usually needs 5 important things. The first is the init function, which is anything that you need to initialize the class, like the device or any other constants. Then you have the initialize function, which actually is going to be called when the Torch server comes up. Here you basically load in all of those dependencies like the JSON files and the model weights and all of that to actually create the model. Then you have the preprocess function, which is going to handle all of the pre-processing you need to do before you pass it to the network. So if you're just passing text in, you first need to tokenize the text into a series of integer tokens using your vocab file. That's what you're going to do in the preprocess step. Then you need the inference step, which is the inference function, wherein you'll basically call your model with the input. And finally, you have the post-process step, and that gets called after your model has outputted something and you want to post-process it, like convert it into like a probability or anything you need to do after the network finishes running. And that's it. After you have the handler.py file, all you need to do is to run this torchserve command, and bam, your torch server is running. And then to call this torch server, all you need to do is just interact with HTTP requests like this one, where I'm doing a curly request and I'm passing some text through a text file, and here you see I'm getting a sentiment score. You can basically call this API endpoint from anywhere and it's going to work. TorchServe takes care of all the handling of the batching and the resource management, as well as keeping the model loaded and warmed up so that incoming requests can be easily and very efficiently handled. Alright, so you have learned a lot in this video. You've learned about tensors, different ways to manipulate tensors. Then you learned the core of PyTorch, which is the auto differentiation engine. You've learned how to apply those concepts into a linear layer and train it from scratch. And then you've learned how to scale that into more complicated network for text, for images, even write custom loss functions, how to deploy models, observe them, how to deal with uncertainty. You've learned all of that, and now it's time to apply them. I have a host of videos. You can obviously have a look at them, but the best way to learn PyTorch, or for that matter any other skill, is to apply it. So I urge you to go make some projects. But before you go, I have a bonus thing for you for additional powerful libraries that you should probably also know about to improve your skills as a deep learning scientist, deep learning engineer. So here is a list of powerful libraries that you can also learn after you've learned basic PyTorch. The first one is PyTorch Lightning. It contains a lot of convenient utilities that allows you to build on top of PyTorch, especially the trainer API that makes it very easy to introduce things like gradient clipping, gradient accumulation, and more. If you're looking to train on a multi-GPU distributed setup, you should also look at Hugging Face Accelerate, which is a great library to actually scale your training. For hyperparameter optimization, you should look into Optuna. And there are a lot of libraries that are specialized tools for training models in specific domains. For example, tokenizers and transformers from Hugging Face are great for training and fine-tuning NLP models. There's the diffusers library also from Hugging Face that is great for stable diffusion, and it has a lot of applications of UNet. For computer vision, you have the Argumentations library, and that one is a must-have for augmentation. For reinforcement learning, you have Stable Baselines 3, which has a lot of great implementation of the top algorithms. For deployment, I'll also look at Onyx, which is a standard format to represent machine learning models, and it allows you to use your PyTorch models or any other framework models and deploy them without actually loading PyTorch. For interpretability, there's a cool model called Captum, which I've used only recently, and that is a pretty cool tool, and they provide a host of great interpretability methods. Finally, don't forget scikit-learn. Sometimes you just need a simple model to do linear regression or logistic regression or random forest or something. You probably don't even need PyTorch for that. Just use scikit-learn. Alright, so that's my time. I hope you enjoyed this video. Hope you learned a lot from it. Do let me know in the comments how that went for you. I'll see you in the next one. Goodbye.